Hi everyone, my name is Bogdan and this is Nico. We are working at Databricks in our Amsterdam office. And today we are going to show you a bit more some insights into our release process and the tooling and the infrastructure that we built in order to make sure that these releases are fast and reliable at the same time. Before going into the actual presentation, a few things, a little introduction about ourselves. I've been working in the area of big data and infrastructure for big data processing systems for some time, doing my PhD at Delft and with some industry interactions as well. And that's before I moved at Databricks last year, where I work in one of the performance teams with a focus on Spark SQL. And
yeah. Hi, good morning everyone. I'm Nicolas Poggi. So I also work at Databricks with Bogdan. I'm tech lead of the Spark benchmarking team, the team that makes sure that every new Spark release is fast and reliable. And before that, I was working here in town in Barcelona, actually, so it's quite nice to be back at the Barcelona Supercomputing Center. And the projects I've been working in the last 6 years was pretty much optimizing the Spark and Hadoop stack for the cloud. So I've been benchmarking the systems for a number of years now. And yeah, let's start with the talk.
Cool. OK, so at the core of our system, there is Spark. But in order to build and deploy Spark into production, we actually have to interface with two very different worlds. So on one hand, we have the developers and all the CI tooling that is required in order to build and release Spark. And on the other hand, we have to swiftly integrate Spark with all the cloud technology, so to make it run in the cloud. And there we have to integrate it with different storage systems, with Docker technologies. We have a cluster manager that deploys isolated instances of Spark in different clusters and so forth. And of course, at the end of the pipeline, we have our customers, and they have quite a rich array of very different applications from many industries. So this is kind of like the high-level representation of our ecosystem. When it comes to our release process, it is somewhat dependent to the open source release of Apache Spark. So as you see here in this chart, the runtime 4.3 release incorporated Spark 2.3. And we are planning in our 6.0 release to incorporate Spark 3.0. The release process is it's a normal cycle. So we have a period of time in which we are beta testing the release, and then before providing support for it. And there are like two different types of support. We have some releases for which we provide like full-time support before being deprecated. What's also interesting is that at any point in time, basically, if you cut this graph, we have to provide support for for multiple releases at the same time. And of course, our goal here is like to make this release process as automatic and frequent as possible. OK. Apache Spark is quite popular, and actually we receive hundreds of commits like on a monthly basis. And basically this means that every week there are like dozens of contributions. At this phase of development, it's clear that that mistakes are bound to happen, and we want to make sure that the releases that we make do not contain errors that will reach our customers. So that's what we're trying to do, is to prevent these mistakes to go into production. So unit testing is quite the obvious choice in terms of making sure that the product is correct. And we did an analysis of the current state of the project, and it turns out that there is a tremendous work that is done by all the contributors in terms of unit tests. So basically, for every line of code, there is a line of unit test. The question that we are asking here is that, is this really enough to have like a very good coverage of what means the entire Apache Spark SQL project? And to answer that, I would make the transition to how Apache Spark operates. And if you think of the multiple dimensions that you need to explore with testing, like there are like at least 200 built-in functions, and then there are different configuration parameters that need to be tuned depending on which hardware you're running you're running Spark and deploying it. And some of the code paths are triggered, of course, only with certain data sizes. So, and these are kind of very difficult to capture in unit tests, and you're losing a lot if you're focusing only on unit tests. And basically, what happens is, despite the tremendous effort, you're only scratching like some parts of this multi-dimensional design space. So we are definitely using the current methodology. So we are building on the testing pyramid that everyone is familiar with. And I'll tell you a bit more of how we extended this pyramid. So we have different types of specialized testing. So macro benchmarks, basically think about standard benchmarking suites like TPCDS or TPCH, where we run synthetic benchmarks on like real deployments. We also have micro benchmarks where we kind of target a particular component in the system, so like to monitor, like for instance, the throughput of the storage system. We have failure with testing, in which we artificially inject failures and see how the system is running. Plan stability, it's very, so the optimizer kind of has this, it's typically targeting the optimizer to make sure that the plans do not change drastically from one release to another, and if they change, we need to kind of understand why they changed. Stress testing, and we have like also customer workloads, which are more, they are trying to emulate what the customers are running. So they're similar to the macro benchmarks, but they are not synthetic. And finally, we also have fast testing. And here we are trying to randomize and to explore the design space as much as possible. So in this talk, we are going to focus on fast testing and macro benchmarks.
Okay, so how this pipeline looks like. It all starts, if you see here on the chart on the left-hand side, it starts with a developer submitting a new PR to the open source project. So when a new PR is in the system, it triggers a build that produces new artifacts. What are these artifacts? So it's a Spark version along with a container and an operating system where you can deploy it in the cloud and actually build a cluster from that and start running a Spark application on top. So there, what we do is we run testing, what these PRs are in the review stage, and we do both correctness and performance testing of these PRs. And the Spark jobs that run produces several metrics from CPU usage, job times, the different tasks that Spark has. We have all those metrics, and on top of those metrics, we analyze them, and we apply some rules and policies to see if we actually need to trigger an alert. So let me zoom into this last part. So we get a stream of events, which are all these metrics, like how long it took a Spark job to complete. And once it is triggered, but it reaches one of the rules and policies, we need to see if this is really an error or a performance regression. So for that, we try to scope it down. Was it an out-of-memory error, so the job failed completely, or was a resource just more highly used than in previous version? So we try to classify the impact, the scope, and we try to correlate it with other errors. For example, if you have 3 warnings for the same job, that might mean actually it's an error happened in that job. So we also try to correlate different events happening in the job. And if it's a failure, it follows the route of here correctness on the top of the chart. And if it's a performance regression, it will go through the performance analysis tools. In any case, for both correctness and performance, we need to try to root cause this automatically to save engineering time and effort. And what this means is actually we try to test the same job that failed again, maybe in a different cluster size with more nodes, fewer nodes, a couple of times to make sure it was not a false positive, so a false measurement due to variability, for example. Then we try to automate gathering profiles. So we will gather resource utilization profiles. So in case it's not a false positive and we actually need to alert a human, he will have all the information needed. In the case of queries, we also try to minimize them to see, to try to reproduce the error with the fewest amount of lines and SQL operators to make it easier to report and debug.
Okay, let's move to the first part of the presentation, the correctness. So the methodology that we're using is inspired by previous tooling in terms of correctness testing, and one such example is like the SQLite. There are like two different categories of tests: anomaly testing and fast testing, and each of which has like different components. What I want to point out here is that both testing and performance testing have been raised a quite steady interest during the past 10 years. So we've seen that the number of questions on the Stack Overflow is quite constant, and people are interested a lot into this type of testing. So before explaining our SQL fuzzer, I would first make a short presentation of the Spark SQL engine. So what lies behind the scenes? It's quite a typical database engine that takes the query, it maps it to an abstract representation, a tree-like representation, and then it transforms that tree structure through it passes through multiple stages, and it transforms it into a plan that can be executed in a distributed cluster. So these phases of transformations, there are like 3 of them. The first one is the analysis, in which it's figuring out that the query that is written by the user is correct, is referencing like the proper tables. Then this is mapped to a logical plan, which basically tells you what computations you need to do, but it doesn't tell you how to do them. And then after several optimizations, we end up with a physical plan that explains and basically annotates the tree with instructions on how to actually perform those computations. And then there is a cost model involved, because you may end up with like multiple physical plans, and you want to pick up the ones that is the cheapest and faster to execute. And we do code generation and obtain the RDDs. Which are distributed by design, and they can spawn on multiple machines in a cluster and run in parallel. So with a random query generation, basically what we want to do is to take a random query and then run it against different database systems. And one such reference database system that we are using in our testing is Postgres, that provides the strongest correctness guarantees. But on the other hand, we are kind of by doing this comparison between Spark and Postgres, we are kind of limited by some missing operators that Postgres doesn't have, and they're in Spark. Like I mentioned, there are like 200 built-in functions. So in order to fill that gap, we have actually enabled testing between different Spark distributions. Because the design space is so large, so you can just toggle on and off optimizer rules, for instance, or you can tweak like a range of values for a particular parameter. So there you can get like very different behaviors on different instances of Apache Spark. So this is kind of what we are doing at a high level. We are comparing Spark versus Spark, different distributions, different releases, different configurations of the same releases, and at the same time, to make sure that things are really correct, we go back to Postgres with a limited, with some restrictions on the dialect. So before generating the query, we need some random data. We are basically the scheme in which we use to generate the data. It's quite simple. We are randomly picking a number of tables, and then for each of those tables, we are drawing like a random schema. So we have like a bag of supported types, and then we start filling in each of the columns with random data. So it's as random as possible. But one interesting aspect is that most of the time we don't really use large data sets. So what we want here is kind of execute as many queries as possible in a quite short amount of time. But we don't really increase that much the data size. And from our experiments, it's been we saw that it's quite effective even if we are using small data sizes. So for the query generation, basically, the SQL query has like this recursive way of in which it can be expressed, right? So a query consists of like multiple clauses. You may recognize many of them. So you have like the select. You can put their filters, aggregations with these clauses. And each of these clauses kind of consists of expressions, and expressions can be like references to tables or to some column names. But also they can be functions, and functions can contain other queries as well. So this is kind of how the recursive model is generated. So now, if we look at these clauses, we actually realize that not all of them are mandatory. Some of them, like select or from, those have to be like in every query. But clauses like union or group by or filters or order by, these are optional. So what we do is that we assign like independent weights, and then we are drawing from this set of clauses with that given probability. Another aspect of the SQL language is that you can actually have different join types, for instance. And in that case, we use interdependent weights. So we are selecting with a higher probability the inner join, because it's like the most popular. But we also draw, with a lower probability, like full outer joins or right to the joins or left joins and so forth. In the same way, we also can have multiple types of functions, right? So you have analytic functions, aggregation functions, and like basic arithmetic functions, and there we also use some interdependent weights to generate them. Okay, so as I said, when it comes to randomized testing, we're interested in generating as many queries as possible, and to also have like a very good coverage. So we are looking for those cases that typically you wouldn't write alone. You're not going to write a query that is generated randomly on your own. So we are looking for corner cases of the SQL language that do not pop up that frequently. So this is like an example of query that was reported as a correctness issue with this fuzzer. It was found on, like I said, it was found on a relatively small data set, so just 2 tables, 5 by 5 in size, and also very fast. So like within 10 randomly generated queries, we ended up with this result. The error that was reported, this means that there is an error in the analysis phase. So we are also interested in kind of have like this triaging phase of these errors, because you can get a lot of stuff coming up out of a random tool. And we have like a way of triaging these types of errors automatically. Speaking of this example, I wouldn't try to make an effort to understand what the query is doing. So there's a lot of random stuff there. But you can easily identify some of the clauses, like some of the main elements of the query, and you can map them to like an abstract representation quite easily, right? So we have a join between 2 tables, we have a filter on top of the scan, and then we have like an aggregation, right? So to kind of ease ourselves into doing this debugging and figuring out what's going wrong, as Nico said, we're trying to minimize this to a much simpler form. So we start eliminating things that we kind of know that they are not the problem, or at least to kind of put some red flags on the operators that may be problematic. And in this case, if we look at the filters and at the projections, those are kind of our first guesses that something may be wrong there with a double Coalesce, with the nested Coalesce functions, and with the filter that has decimals and so forth, and the cast as well. So we are trimming a bit this query. So we eliminate the join. We see that if the problem reproduces again. And actually, we end up with this minimized query. So the problem here was that the optimizer is flattening the nested Coalesce functions, and basically is not matching anymore the group by expression. So this is why it throws an analysis error. And although it kind of seems like a very corner case, it doesn't. I mean, you wouldn't naturally write a nested Coalesce functions. But it's quite interesting because it raises an issue with a more general issue, right? It may be popping up whenever you have like a group by expression that can be further optimized, right? So it may have like a broader scope and impact. Another example, this is a simpler query. So with the lead function, we have just a select from and a dummy filter. And here, in this case, it's interesting because we got like a mismatch in the returned answer. So we see that on column 3, the results are not the same. We did kind of a similar thing. We tried to minimize this query. So here, we have just a project, a filter, and a scan. And the problem that was here was that using constant input values broke the behavior of the lead function. So basically, this is a known issue. It has been merged a while ago in open source Spark as well.
Okay, so when we talk about testing, we usually need to talk also about coverage. Coverage is the expanse of how many of all the possible things that we can test are we testing. So this chart here shows on the x-axis from 1 to 500 randomly generated queries. So we generated 500 queries, and we run them one after the other. This is on a single node instance. And on the y-axis here, I'm showing the distinct number of physical operators, like it could be sort, aggregate, and expressions. And expressions would be like an or, an equal, a like that you will have in your queries. And we can see that between 500 queries, we actually reach pretty much, we have seen we reach a steady state, and we have seen most of the different expressions and operators. Just for example, these are the top expressions and operators produced by the random query generator framework. And what's important here is that these 500 queries run in less than 15 minutes. So this means that if we have a new PR, a developer submits a new work, we know that within 15 minutes of time, we can test most operators. Of course, this doesn't mean that we're actually testing them with a large amount of data or that they perform well, but we can make a trade-off in test time and expected results, because we can be running random queries for days trying to trigger an error, but we need to know where to have a cutting point. Saying so that we're not testing here with a large amount of data, we can switch now to the performance part of the presentation. So for testing performance in Spark, there are several available tools besides the database specific ones. We make a lot of use of the Spark SQL perf library. So it's a public GitHub repo. You can build this library yourself, and it's pretty much a wrapper and helper to run the standard database tests like TPCDS, TPCH, and you can expand it with more queries and examples. It also provides some dashboards. We're going to see some dashboards in the next couple of slides. And also the Spark code provides a micro benchmark framework. So if you're working on a new feature in Spark or improving a feature, you can test the baseline as the previous behavior and the new behavior, which hopefully will be faster than the one you had. And you can submit this along the code and so that the community can review the PR. We also use some Java-specific tools like profilers. We use the async profiler, which produces some flame charts, flame graphs. This is an example of a CPU flame graph. flame graphs are pretty much stack traces, so profiles of how the code executed. But the redder they are, or the darker the color, it means that more calls have gone through that loop. We're going to look at some profiles later on. So let me take you through an example. I call it a journey. So last summer, we were testing DVR 5, and this was going to include a Spark to 4. And this was around August last year, so in summer. I don't know who thinks about putting a release during summertime, but it was fun. And here in the dashboard, here in the top chart, lower is better, so it's time in seconds. The blue curve is pretty much stable. You can see that's our 4.3 release with a Spark to 3. And then we have this continuous first orange line, and then the green line here. And this was caused by changing our development branch, pointing to Spark to 3 to Spark to 4. And we found that there was a 15% regression when we tested the beta version of Spark to 4. And 15% for us is tremendous, so it's a very nasty regression. Every release, we try to increase performance by 1 or 2 points, or every feature, it's like improving just marginally the performance, and seeing a 15% regression, it meant like we were going to have a busy summer last year. And so the tooling also helped us see what queries might be the most affected ones, so that we start looking into problems where we're more likely to find them easily and report them back to the developers. So this is an example of query 67 of TPCDS. The query usually runs in 5 minutes in Spark to 3, and in Spark to 4 now it's running in 6 minutes. So it's almost 20% regression. This is not a fast query, so it takes more than 1 minute to run, and this means that this is a real regression. So the first step is we want to really know if this is a false positive or not. And so we confirmed that this was a regression, and the next step was looking into the profiles. So this is a flame graph for this query 67 of one of the Spark executors. A frame graph by itself doesn't help you much unless you want to zoom in and start drilling into the chart and you know what you're looking for. Usually what we need to do is to compare the previous state to the new state. So here we have a Spark to 3 and a Spark to 4, the same query run on the different clusters with the different versions. And I don't know if you can spot the difference between these two charts. They look quite similar. The good thing about Flame Graph is that there are SVGs, and you can zoom in and navigate through them. So they're quite useful. But visually, it's a very tedious process to do this visually and finding the difference between two images. So if we zoom in slightly here, I don't know if you noticed, but there's a new stack trace, and a small stack trace or peak in the Spark to 4 one. So there is indeed a difference in execution, not a significant one that would change the execution flow. But luckily, we have some tooling that we don't have to do this process visually all of the time. So there's also a Framegraph diff tool. This is the result of the Framegraph diff. You pretty much get two images, you diff the profiles, and it builds you another flame graph highlighting the difference. So here on this chart, anything that is in red, it's slower in the new version. This is a zoomed in to the affected area, and anything that is white actually is new on the target image. And so the next step would be to actually try to identify what's different. And we start getting some clues that the hash UTF-8 string function was changed. Also, the hash and saves byte flock was changed. So this was looking like it was a memory-related issue, or something on the hashing functions and related to UTF-8 strings. So the next step is to root cause is finding possible PRs that might cause this. So we go into the Git log and we do a bisect. We might run different. We might build different images from every PR. And there was one that refactor the memory block API, so touching exactly the functions we were seeing in the profile. So the next step is to actually prove it, to come back to the developer and say, hey, this new code might be regressing. So we build a micro benchmark, just testing the UTF-8 string function, and we found that in this case, the hash and safe bytes went from 40 microseconds to 140 microseconds. So over 3 times more slow, and of course these are microseconds. You might think, oh, it's not that much, but imagine you have to do this, apply these functions multiple times to every string on the data set that you're analyzing. It adds up to a lot. So the next step is actually reporting back to the PR, to the community, so the developer would do a fix. But by the time Spark 2.4 was about to be released, this was not really fixed, so the whole PR was reverted and still is under work. So it is a journey to get a release out. Getting a major release out took more than 1 month of testing, especially when you have multiple components, you have you're working with the community, etc. We're expecting something similar for Spark 3 soon. And we started with 15% regression. We went down to 5 after some work, improving some of the new features in the Spark 2.4 to 5, and then we got it to an improving state. There is a lot of manual work that we want to automate and make it the whole process as efficient as possible. So in Spark 3, we actually don't have to spend 2 months testing and iterating related to performance. It's a long journey, but it pays off quickly. Like here on the chart, just as an example, we have the Spark. This is the speed up of the Spark 2x branch that we measure in our system. And we see that from Spark 2.1 to Spark 2.4, query times have improved. So they have been reduced by half. So 2x performance improvement. And we're already testing Spark 3. We know that it's faster than Spark 2.4, and not all of the major features have been merged yet. So testing the product really help us improving this performance over time. And in less than 2 years, we get a reduction of half the query time. So that's quite significant. And to conclude, Spark is not this only this Apache project that you can download and build on your machine. To have it running in production, you actually need to run it in a cluster environment with several nodes. There's the operating system, the libraries, the JDK. So unit testing and integration tests are not enough, and we're advocating to keep building Spark-specific tools to automate this continuous integration pipeline. So the idea is that we can develop new features faster, test them, and have higher quality products out of the market sooner. Yeah, and with that, I'd like to thank you for your attention, and we're happy to take some questions. So, questions? Okay, well, thank you. We'll be around if you want to know some more details.
Thanks.